Hello everyone. In the last lecture, we had discussed about the transistor biasing, in particular voltage divider bias. In today's lecture, we shall know about the concepts of leakage current, stability, what is meant by thermal runaway, and the concept of heat sink. Now, we know that the transistor can be forward biased. That means base emitter junction will be forward biased and collector base junction will be reverse biased to have a faithful amplification and for the transistor to work in the active region. When it is reverse biased, we come across a very important parameter and a concept called as leakage current. Now we shall know what is meant by leakage current. So in the normal operation, as we all know, the base emitter junction must be always forward biased. So when it is forward biased, the majority charge carriers flow and the collector base junction must be reverse biased. So the current conduction in the transistor is both by majority charge carriers and minority charge carriers. Just observe the diagram here. This is a NPN transistor. In N region, electrons are the majority charge carriers and holes are minority charge carriers. The base is made up of P-type material, therefore holes are the majority charge carriers and electrons are minority charge carriers. In collector, it's made up of N-type and therefore electrons are majority charge carriers and holes are minority charge carriers. Now when the transistor terminals are biased, the charge carriers move from one region to another region. So when it starts to move from one region to another region, so it starts from emitter, the emitter emits the charge carriers and it reaches the collector section. So majority charge carriers move up to collector section. Now let's observe in this diagram. So this is a common base configuration. Now base emitter junction must be always forward biased in order to make the majority charge carriers move. The majority charge carriers move from emitter region to base region. Few of them will recombine in the base and gives rise to base current IB, and remaining 90% or 95% of the charge carriers move on to the collector section and they reach the collector and this gives rise to collector current. But the second section, that is the output section, is reverse biased. So when this is reverse biased, the depletion region widens here, and as the depletion region widens and we go on increasing the output voltage, the charges inside the depletion region, they start to increase. So that charge is called as minority charges. So this gives rise to a current called as leakage current. So the discussion of today's lecture would be the different types of leakage current. Now we shall see some of the concepts of leakage current. So as I told you, the emitter junction is forward biased. As a result, most of the charge carriers move from the emitter region towards the collector junction, and this gives rise to a current called as majority charge carriers or majority current. So the current flows into the collector, it is called as the collector current, which is because of majority charge carriers, and we denote it as IC majority. Along with that, there exists a reverse leakage current because of the reverse bias that we are going to apply onto the output circuit. There is a small current and that current is called as the leakage current or reverse saturation current. That also results in a small current at the collector section and we name it as IC minority. The total collector current at the output, so because of the majority charge carriers from the input side and the minority charge carriers which is developed because of the reverse bias here, there is a total flow of current into the collector section, and therefore we can say that the total collector current at the collector would be because of both majority charge carriers and the minority charge carriers, and we write it as the collector current in total would be IC majority plus IC minority. So this minority charge carriers is denoted by a particular alphabet. So we write this as ICBO. Now we shall know what exactly this ICBO is. Now we shall know the two different types of leakage currents that are present in transistor. To know that, we can take either of the modes. I will be taking common base mode for the discussion now. So we will be knowing about transistor leakage currents. Now I will draw a transistor in common base configuration. Base terminal is grounded, and this is the emitter terminal and this is the collector terminal. So this is the output circuit and this is the input circuit. Observe here, when we forward bias, the majority charge carriers move from emitter section into the collector section. We call this current as IC majority. Current due to the forward biased input section gives rise to a current which is called as majority charge carriers. So we get the output current as IC, the input current as IE, because base is grounded here. So the current is of two types. There are two types of collector current here. One is IC because of forward biased section, and we call it as IC majority. Because of majority charge carriers. We also get a current because of the reverse bias that we are going to give. This is NPN transistor. Therefore, I will be connecting positive terminal to the collector section. So this is VCC, right? So now, because of this, I am going to get a collector current, and that current I can call this as IC, which is equal to ICBO, which is called as the leakage current. So this would be the sum of IC minority charge carriers. So the total collector current IC, total collector current would be equal to IC majority plus IC minority. So how to calculate this IC minority? To get this IC minority, we will keep this emitter terminal open. We will keep the emitter terminal open and we will just apply the bias onto the output circuit. So when the emitter terminal is open, what the collector that I am going to get here is called as the minority current, and we read this as ICBO. So I can write this as ICBO, and this is read as the current at the collector with the current at the output, that means between the collector to base when the emitter terminal, the third terminal of the transistor, is open circuited. So this is the leakage current in common base mode. So the leakage current in common base mode is indicated as ICBO. So ICBO is a leakage current in common base mode. It is read as the current between collector to base when emitter terminal is open. This is one of the type of leakage current that we can see in common base mode. So we have IC majority and IC minority. So in IC, we can know that the majority charge carrier, if you calculate the gain of the transistor, the current gain of the transistor in common base mode is alpha. So alpha, I can write alpha is equal to the ratio of output current to input current. This is IC divided by IE, IC divided by IE. Or if I want to know what is my collector current, IC would be equal to alpha times IE, alpha times IE. So this is the current because of the majority charge carriers. So I can write this as IC total is alpha times IE plus ICBO. So this is the total collector current which appears at the output section in the common base configuration. In the common base configuration. So the transistor leakage current in common base mode is called as collector to base leakage current, and we call it as ICBO. And this we have the emitter terminal open. When emitter terminal is open, the carriers injected to the collector section is 0. We are focusing only on the leakage current, therefore we are making it as 0, or we are making the emitter terminal open, but in practice it will not be open. And here, just because to know what is the leakage current, we are going to do this, assume this. So now ICBO will also flow in the direction of collector current in the same direction. IC is equal to ICBO, and IC also will be coming because of the majority charge carriers. So alpha times IE is a part of emitter current that reaches the collector and becomes collector current, as well as because of the reverse bias we have ICBO, that is called as the collector to base leakage current, and this collector to base leakage current will double at every 10-degree rise in temperature. So we have the total current IC is equal to alpha times IE plus ICBO. This leakage current ICBO depends on two components. One is temperature, other one is reverse bias voltage. So in this, when you consider the temperature, the current due to the thermal generation of electron hole pairs, this will double for every 10-degree rise in temperature. So ICBO will increase, or it will double for every 10-degree rise in temperature. Next one is the reverse bias voltage. As we increase the reverse bias voltage, the current also will increase. The reverse current also will increase. So as this reverse current increases, this will give rise to ICBO. So these are the two important components that is going to affect the reverse leakage current. Now we shall move on to the next type of leakage current, which we call it as ICEO. So this is a leakage current which can be seen in common emitter configuration. In common emitter configuration, the leakage current is called as collector to emitter leakage current when the base terminal is open. So this is the input section, therefore we are opening the input section. When we open the input section, there is no base current appearing here, therefore when base is open, we are going to consider only the leakage current in the output section. But we will have to consider the total collector current. When we want to consider total collector current, we do apply forward bias here. When we apply forward bias here, we get sufficient current reaching the collector, sufficient charge carriers reaching the collector, which gives rise to IC majority, that is called as the majority charge carriers because of the forward bias junction, as well as the leakage current because of the reverse bias. So the collector current flowing through the base terminal, when base terminal is open, we call it as ICEO. So this ICEO is a leakage current in common emitter configuration. The total collector current would be equal to, IC is equal to majority current plus minority current. So in common base mode, beta is the current amplification factor. Beta is equal to IC divided by IB. So if I take IC will be equal to beta times IB plus the leakage current ICEO. So this is the expression for total collector current in common emitter configuration. Now let us see on what factors it depends. So ICEO depends on two important parameters again. One is the temperature, as we saw in common base mode. So the current due to the thermal generation of the electron hole pairs will double for every 10-degree rise in temperature. The second point is the reverse bias voltage. This, as the collector voltage is reverse bias, reverse saturation current ICEO will start to flow through the collector terminal, and it will start to increase with the increase in reverse voltage. So this is another factor or component which will lead to the increase in ICEO. So we know that the transistor current equation, we are going to find the relationship between ICEO and ICBO. So now here we know IC is equal to beta times IB plus ICEO, and IC is equal to alpha times IE plus ICBO. These are the total collector currents in common emitter mode and common base mode. And we also know the total current in the transistor by transistor current equation, IE is equal to IC by IC plus IB. Rearranging and solving these, we can arrive at an expression that ICEO will be equal to beta plus 1 ICBO. So this is the relationship between ICEO and ICBO. We shall now discuss about a very important concept in transistor which is called as thermal runaway. So this is linked with the leakage current. So as we have just discussed about the total collector current, so it is represented by IC is equal to beta times IB plus beta plus 1 ICBO, where IB is the base current and ICBO is the leakage current. So this is the reverse saturation current. It depends upon the minority charge carriers. So the cause of reverse saturation current is the flow of minority charge carriers. So in p-type semiconductors, electrons are minority charge carriers, and in n-type the holes are minority charge carriers. This minority charge carriers entirely depends upon the temperature. As if we increase the temperature, the concentration of minority charge carriers will also start to increase. As this increases, this ICBO or leakage current will also increase. In this expression, as the minority charge carriers are going to increase, this factor will increase. As this factor will increase, the whole of beta plus 1 ICBO will increase. As this increases, as beta plus 1 ICBO increases, the collector current also will increase. So this, we can say that as the temperature increases, the collector current also will increase because of the increase in ICBO. This will see to that, or we can see to that, the collector current is directly proportional to temperature. As temperature increases, the leakage current increases. As the leakage current increases, the total collector current will increase. Now, what is meant by thermal runaway? So this is a very important concept wherein the transistor is going to get distracted or burnt out. So transistor is going to burn out. The self-destruction of transistor is called as thermal runaway. So we shall see how exactly it happens. As I told you, as the temperature increases because of the reverse bias that we have given. As the reverse bias voltage is increased, the temperature of the junction increases. As the temperature is increased, the leakage current ICBO is directly linked to the increase in temperature, therefore ICBO will increase. As ICBO increases, the total collector current increases because IC is equal to beta IB plus beta plus 1 ICBO. So if IC increases, again at the junction of the transistor, the temperature will start to increase. So as the temperature once again increases, ICBO increases, ICBO increases, IC increases. This is a repetitive process, or this process is cumulative, and this keeps on repeating. At one fine time, the temperature of the junction will be very, very high, so that the collector current or the charge carriers will be very high, and therefore the transistor will burn out. And this is going to get the transistor into, this makes the transistor go into the destruction. Therefore, we define thermal runaway as a process as the self-destruction of the unstabilized transistor, which is called as thermal runaway. They will ask you in the examination what is meant by thermal runaway. Now, what are the mitigations of thermal runaway? How can we reduce the changes in thermal runaway? How can we look into make the transistor to be stabilized? So for that, we are going to have the negative feedback in the transistor. This can be achieved by connecting an emitter resistor across the emitter terminal. That's what we have done in voltage divider bias. In voltage divider bias, we have a resistor connected across the emitter terminal with respect to ground. This will make, or this will avoid the negative feedback, or it can make the transistor to be in a stable condition. So the introduction of negative feedback is one of the parameters which will avoid thermal runaway. Next one is using heat sinks. So we shall be knowing about what heat sinks are. Now here the flow of collector current produces heat. Because of the heat produced, the temperature will increase. As temperature increases, ICBO leakage current increases, the leakage current increases, the collector current increases, and this is a cyclic process and it is cumulative. As a result, the transistor will burn, and this will lead to the self-destruction of the transistor, and this phenomenon is known as thermal runaway. We shall now discuss about another important factor called as the stability factor. How do we define the stability factor of a transistor? So we know that the main aim of the biasing circuit is to stabilize the transistor's operating point or Q point against any variations in its parameters. What are the parameter variations? It can be the input voltage, or it can be the beta or current amplification factor. So this will start to change with respect to the increase in temperature. So making the transistor independent of any parameter is known as stabilization. So we can define stabilization as making the transistor independent of other transistor parameters. Now we come across a very important concept called as stability factor. How do we define this stability factor? So it is defined as the rate of change of collector current, a small change in collector current, I can write this as delta IC, to the leakage current, or with respect to leakage current ICO. So this ICO, I am not particularly mentioning it as ICEO or ICBO. I am taking in general this as the leakage current. So the stability factor, it is abbreviated as S. S is equal to the rate of change of collector current with respect to the leakage current ICO at constant VBE, that is input voltage, and current amplification factor beta. This is how we define the stability factor S. So this stability factor measures the stability of the system. The lower the value of S, stability factor, more stable will be the system. So we should have the lesser stability factor, lesser value of stability factor. If I say I have two transistors of say stability factor of 8 and second transistor of stability factor 5, then it's better to choose the transistor which has a stability factor 5. So I'm going to have a stability factor. That stability factor is just a number. So it is going to tell you, or it is going to see to that the system is going to be very, very stable. Now, so this ICO is temperature dependent, and this has to be taken care of. So we have stability factor defined as S is equal to delta IC by delta ICO with constant VBE and beta. There are other two types of stability factors that are also defined. We have S dash and S double dash. So in S dash, this is a type of stability factor where beta is in the denominator, IC divided by beta at constant ICO and VBE. So this is one type of stability factor. Another type of stability factor, S double prime, will be equal to IC divided by input voltage VBE with the other two parameters, that is ICO and beta, to be constant. And in our discussion, we are just focusing only on the S, which is equal to delta IC by delta ICO. Now we'll see what is meant by heat sink. So heat sinks is one of the most common form of thermal management technology in machinery and even in natural systems. So whenever a system gets heated up, this is the main area that we need to address. So we have to cool it down. So these components means I'm talking about heat sinks. They are ubiquitous, that means they are found everywhere, that they are very easy to overlook it. That means even those who are familiar with the technology, they do come across a very important parameter or factor called as heat sink. So now, the transistor that can handle larger power dissipates more heat during this operation. The heat that is not dissipated properly inside the transistor is going to damage the transistor. So now this heat which is provided or which is there accumulated inside the system has to be radiated or taken out from the system so that the transistor will not burn or any other electronic component will not burn. So this is the main area we need to focus at. you can just look here. This is a diagram, or this is the image of a motherboard. There is a very important component in the motherboard which is called as heat sink, right? So this heat sink, you can see here, there is lot of heat produced inside the motherboard. As we use the computers get heated up. This heat has to be removed from the system so that the operation of other components becomes very reliable. Otherwise there might be a lot of heat and the efficiency of the system goes down. So you can see this heat sink is going to absorb all the heat and it is removing and sending out from the particular area. So this is the job of heat sink. So how can we define a heat sink? So it is a device which absorbs unnecessary heat that is generated in a transistor and radiates to the surrounding and safeguards the device. So this is the main motto of using heat sink. So this is a device which will absorb all the heat that is there in the surrounding region and it will give it out into the atmosphere. So the maximum power handled by a particular device and the temperature of the transistor, they are related to each other. So here, since the power dissipated by the device causes the temperature to increase, the power handling ability of the device goes on decreasing. So as a result, we need to properly ensure that the heat inside the system has to be eliminated or removed. So these are this is the main motto of using the heat sink. Now let us see what are these heat sinks made up of. Though this is not in our syllabus, we'll just know what exactly is heat sink and from what material these are made up of. The heat sink is usually made from aluminium or copper. So this aluminium alloys are the most commonly used heat sink material, and this is because they cost less and compared to copper, and therefore even copper is used where higher levels of thermal conductivity is needed. So some of the heat sinks, they make use of both copper as well as aluminium. So there are different types of heat sinks. What are the different types of heat sinks? There are many types of attachment that we can do to the transistor. So it can be paste like adhesives, it can be bolts, it can be clips, it can be board locks, it can be press fits, it can be thermal tapes, and it can be also soldering. There are different types of heat sinks available in the market. Is it necessary to remove the heat? Yes, it is, very much. These are the images of heat sink. So this is a thermal pad which is used in CPUs and other computer devices. There's a pad which will be sticked or glued onto the surface to remove unnecessary heat and safeguard the device. So next is an image of a metal paste. This is a paste which will be applied onto the surface which will take out the unnecessary heat. So it can be a gum tape or adhesives, or it can also be a thermal paste. There are different types of heat sinks also. You can just see the image. There are fin type heat sinks, and if you look at the electronic components, you can see most of the heat sinks being attached to the device. So you can see a flat piece of metal. This is also a heat sink where transistors are placed on it and they are attached to it, so that whenever the transistors are put into the circuit, there's lot of heat produced. This heat is getting transferred onto this device and the heat will get easily go out of the particular system and it safeguards the system, and this will avoid thermal runaway. This is one of the very, very important concept of reducing thermal runaway. That means as the temperature increases, the leakage current increases, leakage current increases, collector current increases, collector current increases, again the temperature increases, and the cell, it goes into distraction, which we call it as thermal runaway. So heat sinks will avoid thermal runaway. So these are the different images of heat sinks. So we have a power supply here. So this is a power supply that we are using in our lab. So you can just see here, there is a heat sink that is being attached to this power supply to remove the unwanted heat. So this is a transistor. So you can just see the transistor here, and you can also see that this is manufactured by BEL, Bharat Electronics Limited. So this transistor is being attached to a metal plate. So this metal plate is called as heat sink. So if the temperature increases, this heat sink is going to remove all the temperature out from the particular system. So therefore heat sinks protects the transistor and it makes the transistor, or it avoids the transistor going to thermal runaway. So in today's lecture we discussed about what are the different types of leakage currents, that is two kinds of leakage currents. In common emitter mode it is called as ICEO, and common base mode it is called as ICBO, and we also talked about what is meant by thermal runaway, and we also discussed about the stability of the transistor, so that we are going to make the transistor fixed exactly at the center of DC load line, and it is not going to shift. This parameter we just discussed about the stability of the transistor, as well as we discussed about heat sinks, which is going to avoid the damage of the transistor, which is known as thermal runaway. Thank you.